All right, so in this first problem, we're given a graph of the derivative of a function, capital F, and we're told that the value of the function at 0 is 7, and we're asked to sketch a graph of the function f and give the coordinates of all the local maxima, minima, and identify the inflection points. Okay, so a key thing here to know, this is the derivative, okay? So this is telling us what the slope of the function f is at any given point, okay, because it's the derivative. The first thing, though, I would recommend doing on this problem is just to create a little table of values, because there are certain values of the function f that we can just figure out. I mean, we've already been given at 0 that the function is 7. Okay, so we know that if we were going to graph this capital F function, it will pass through the point 0, 7. Okay, and then we can use the areas that are given here to find the other points, right? Because the area under the curve, right, under the derivative curve, gives you the change in the value of the function, right, by the fundamental theorem of calculus. Okay, so what we have here at first, here we've got an area of 9. Now, but it's below the curve, so it's actually a negative 9. So if we take the value of the function at 0 and subtract 9, because we're basically adding a negative area, right? So the change in the function is a negative 9. So that means at 1, by the time we get to 1 here, then our function value is going to be minus 2, right? Just 7 minus the area, which is 9. Okay. And then we can keep going from there. If we were to integrate from 1 to 3, we get the change in the function, the original function, not the derivative, but the original function, between 1 and 3, and it's telling us that the change in the function is 5. So in this case, it's above the x-axis, so it's a positive 5. Okay, so now we are at negative 2, so by the time we get to 3, we have to add 5, so we are at the point 3 comma 3. Okay, and then we just keep going. So the next point we can find that's on the curve is at 7. Okay, so we're just going to take the value of the function at 3 and add the integral from 3 to 7 to get the value of the function at 7. And the value of the integral is just 20, so we're just going to add, sorry, it's negative 20, right? The value of the integral is negative 20 because this area is below the curve, or below the x-axis. So we're going to subtract 20, which leaves us at minus 17. Okay, and then finally we've got one more area between 7 and 10, and we're going to add, in this case because this area is above the x-axis, we're going to add 18. So we add 18 to 17, and we end up at 1, right? So we're just adding the integral from 7 to 10 to the value of the function at 7, and we end up with the value of the function at 10. Okay, so now we have a table of values and we can plot those points. Okay, it's always a little bit of a trick to draw graphs with my pen here, but I'm just going to, it's not going to be pretty, but it'll give you an idea. Okay, so there's our axes, and so let me draw a scale on here. I'll try to draw it similar to what I've got. So here's 1 and 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so there's 10, 9, 8, 7. These are the important ones here, right? So, and then I need a scale, and it looks like we need to go all the way down to minus 17, and we need to go up to at least 7. So I'm just going to break this into 5. So this is going to be 5, 10, 15, and this will be minus 5, minus 10, and minus 15. Okay. And now we can kind of start sketching the graph. So initially at 0, we're at 7. So let's say 7 is about, right, it's about here, let's say. Okay, so that's the point 0, comma 7. And when we are at 1, we're at -2. So that's about, let's say here. So this is 1 comma -2. Okay. And at 3, we're at 3. Okay, so where's that? That's about here, let's say 3 comma 3. And then we know the value of the function at 7 is a -17. So I'll put that about here. 7 comma -17. And then let's see, we have 10 comma 1. Okay, so I'll put that about here. 10 comma 1. Okay, so there's some points on our graph. But now we're asked to find local maximum and minimum. So this graph of the derivative also gives us some information about whether the function is increasing and decreasing, right? Because when the slope is negative, the function's decreasing. When the slope is positive, right, which means the first derivative is positive, then the function is increasing. So we can see here, let's see if I could draw a little number line. Actually, maybe I'll draw it down here. Let's draw our little number line and put arrows on. So there's 10, so there's about 7, and there's 3 and 1. Okay. And so you can see the derivative is negative, right? F prime is negative between 0 and 1. So that means the function is decreasing. So I'm going to draw a little arrow to indicate that it's decreasing. Okay. And then between 1 and 3, those values of f prime are positive, which means the slope is positive. So it's an increasing function here. And then between 3 and 7, we're below the x-axis, so our f prime, our slope is negative, so we're decreasing in this region. And then between 7 and 10, all those values are above, so we're increasing here. Okay, that's all we can really tell because we only have values between 0 and 10. So that's going to tell us that where our local minimum and maximum are. We can use that first derivative test to find that this point at 1 comma -2 has to be a local minimum. That's to abbreviate local min. Okay, because the function is going from decreasing to increasing, right? So, and the derivative is 0 at 1, right? So that's a critical point, and it's going from increasing to decreasing, which means, decreasing to increasing, which means that it's a local minimum. Okay. Now our next critical point is at 3, and in this case we're going from increasing to decreasing. So this is a local max. Okay, at 3 comma 3. And then our next critical point is 7. We're going from negative to positive, which means the slope is going from negative to positive, which means decreasing to increasing. Decreasing to increasing means local max, or sorry, local min. Local min. All right. And then finally, we do have a critical point here at 10 because the derivative is 0, but we really don't know what's happening on the other side of 10. Okay, so it can't really tell if it's a local min or a local max. I mean, it kind of looks like it might be a local max, you know, because it's sort of looking like it would, just given the trend, it looks like it would be going from increasing to decreasing. So, but we can't really say too much about 10 because it's an endpoint. Okay. Now, if we were figuring out global maximum minimums, we'd have to include all the critical points and the endpoints. The endpoints at 0 and at 10, we would include that if we were evaluating global maxima and minima. Okay. So, and you can tell. So, this doesn't ask for a global max and mins, but this would be a global. Even though it's not a critical point, right? The value here of the derivative is certainly not 0, but it is a global maximum, right? Because it's bigger than any other point. That value of 7 is bigger than any other point on that interval. Okay, and then it looks like this value down here is also our global minimum, right? This 7 comma minus 17, because it's smaller than any of the other candidates for global minimum. Okay. And then really this endpoint, you know, if you included it, you know, if this was a quiz question and you included it as a global or a local maximum, I wouldn't count it wrong. I'd say, yeah, you're fine. So, but we really can't tell what's going on the other side of 10 because it's not, we don't have enough information. Okay, so let's we want to take, okay, we still have to sketch this graph, right? And we can actually find out some more information about the function from the derivative, because the derivative of the derivative, right? So the slope of the derivative gives us information about the concavity, because the derivative of the derivative is the second derivative, and when the second derivative is positive, it's concave up, and when it's negative, it's concave down, and so on. But we have to look at the slope, not the value of the derivative, but the slope of the derivative, right? Because the slope of the derivative would be the second derivative. So you can see the slope between 0 all the way up to somewhere around 1.9, somewhere around there, right? The slope is positive. So that's telling us it's concave up, right? Between 0 and 2, we're concave up. All right, so that looks like a U, concave up, right? So it's this kind of thing. So concave up and decreasing looks like that, right? It's curved like that. And then concave up and increasing looks like that. Okay, so we have a kind of an upward shaped U. Okay, and then at that, this would be an inflection point. Inflection point. Because we are changing from concave up to concave down, right? Because the slope here is negative, right? And the slope here is 0, right? The inflection points, the candidates for inflection points are wherever the slope is 0. And so the slope is 0 and it's going from concave up to concave down, right? Because the slope of the derivative, second derivative, goes from positive to negative. Okay, so we have an inflection point somewhere around 1.9, and we're concave up. So let's just kind of draw what that looks like. We're concave up, until about 1.9. Okay, and then we switch to, you can see the slope here all the way to about 5 is negative, which means we're concave down, right? So here we're switching to concave down, and so we have something that's going to curve like that, concave down. All right, until we get to about this point. This is going to be another inflection point because the derivative of the derivative, right, the slope of the derivative is 0 at that point. So that's going to be another inflection point at about 5. So 4, 5. Okay, so let's see. We're concave down until about 5. But we somehow have to get all the way over here. So, we can't get the exact inflection point. But let's see if I can just sort of draw that. So it's going to be that, and then about 5 we switch. Let's see, we switch to concave up. Okay, so let's see. We'll call that an inflection point. I'm just going to abbreviate it IF because, or sorry, IP. I'm going to call it IP for inflection point. We'll call it that, and then we have another inflection point here. Okay, at about 5. So just indicating, I'm just indicating where they are. I'm not gonna, you don't have to give the exact points. All right, and then we're concave up because the slope of the derivative is positive all the way up to about, I don't know, somewhere around 9. Okay, so we're concave up till we get to about 9, and then we'll switch to concave down. Okay, so here's another inflection point. All right. So let's see. We answer everything. Yeah, we have the local min and max. Now I could summarize it, somewhere here, but you can see we have local. I've identified all the local min and max, as well as the global min and max. And I've indicated on the graph anyway where the inflection points are, roughly where the inflection points are. And I think that's all we need to do. So there you go.